All right, welcome back to TalkTensors. You know we love digging into the cutting edge of machine learning research. And, well, today we've got a paper that really dives into one of those bottlenecks that's holding LLMs back from their full potential.
Oh yeah, definitely a bottleneck. It's all about speed, really. How do we get these big, powerful models to think through complex problems more efficiently? Especially when we need them to explore multiple different solutions, not just settle for the first one that comes to mind.
And we're talking specifically about this technique called multi-sample inference, right?
Yeah.
Where you have the LLM generate a bunch of different possible answers and then use some method to pick the best one.
Exactly. Self-consistency, for example, where you basically do a majority vote, or best of n, where you have some kind of scoring system to rank the solutions.
Right. The idea is that even if one line of reasoning goes off the rails, if you have enough of these parallel attempts and the right answer keeps popping up, there's a good chance it's the correct one.
Yeah, it's been a really powerful strategy, especially for things like mathematical reasoning, where you need the LLM to really think things through step by step. But the catch is, well, it's slow.
Because you're essentially doing the whole generation process multiple times over.
Exactly. So if you're generating, say, 10 different solutions instead of one, you're looking at, well, roughly 10 times the wait time. And that just doesn't fly in a lot of real-world applications where speed is critical.
So the paper we're diving into today is about a new method for speeding up this multi-sample inference. And it's based on this technique called speculative decoding, but with a clever twist, right?
Yeah, a really clever twist. They found a way to make speculative decoding work specifically for these multi-sample scenarios, and they do it without needing any external resources like additional models or giant databases, which is a big deal.
Right, before we get into the details of their approach, let's set the stage a bit. Why did this whole multi-sample thing become such a big deal in the first place?
So it really goes back to this sort of revolution in how we use LLMs that started, I'd say, around 2022. With the rise of prompting techniques that could really unlock their reasoning abilities.
Like chain of thought prompting, where you give the LLM an example of how to think through a problem step by step.
Right, exactly. And one of the key papers that demonstrated this was by Waite et al. They showed that this guided approach could dramatically improve the LLM's ability to handle complex tasks. And then shortly after that, Koby et al. Took it a step further.
And said, hey, what if we don't just generate one chain of thought, but a whole bunch of them, and then we use self-consistency to aggregate the answers?
Yeah, and that really opened up a whole new level of performance for LLMs, especially in mathematical reasoning.
Okay, so multi-sample inference, it's powerful, but it's computationally expensive. And that brings us to speculative decoding as a potential way to speed things up. Can you give us a quick rundown of how that works?
Sure. So the basic idea behind speculative decoding is to have a faster kind of draft mechanism that can predict a sequence of potential next tokens. And this could be a smaller model or some other quick method. Then the main, more powerful LLM comes in and just verifies those draft tokens.
So it only needs to do a quick check to see if they align with its own predictions.
Right. And that verification step is much faster than having the LLM generate each token from scratch. So overall, you get a speed up. But the researchers in this paper point out some key limitations with the traditional ways of doing speculative decoding.
What are the main challenges they see?
Well, a lot of these existing methods rely on external resources for generating the draft tokens. Like if you're using a separate, smaller draft model as Aliel described in their work, there's a chance that the tokens it predicts might not perfectly match what the main, more powerful LLM would have generated.
So you end up with lower acceptance rates for the draft tokens, and the speed up isn't as good as you were hoping for.
Exactly. And if you're using a retrieval database of previously generated text, which was explored by he et al., just the act of querying that database adds its own latency.
Right. And you also have the added cost of building and maintaining these external resources, whether it's a draft model or a massive database. So the authors of this paper had a brilliant insight. Instead of relying on these external resources, they realized that multi-sample inference itself creates a gold mine of potential draft tokens.
Because think about it, when the LLM is generating those multiple parallel reasoning paths, they often share common intermediate steps, even if the later parts of the reasoning diverge.
So you're basically saying that because all of those parallel paths are being generated by the same LLM, those shared substeps are already perfectly aligned with the model's own knowledge and tendencies.
Exactly. So their method, called SDDSD, dynamically builds a pool of potential draft tokens by actively looking for overlaps between these parallel reasoning paths.
So how does that actually work in practice?
As the LLM is generating those multiple reasoning paths, for any partial sequence of tokens on one of the paths, they take a small window of the most recent token, say, the last 3 tokens, and use that as a query.
And they search through the other parallel paths for any sequences that start with those same 3 tokens.
You got it. And the tokens that come right after those matching prefixes on the other paths, those are the candidates for the draft pool. It's like finding moments of consensus in real time across those different thought experiments the LLM is running.
So they've got this pool of candidate draft tokens. But how do they actually decide which ones to propose as the draft for the main LLM to verify?
Well, they organize these candidate draft tokens into a structure called a weighted directed acyclic graph, or DAG. Imagine it like a network where each unique token in the candidate pool becomes a node.
Okay, I'm picturing that.
And if one token is followed by another token in one or more of the candidate sequences, then there's a directed edge drawn between those 2 nodes. And the more often a particular token follows another across those parallel paths, the stronger the connection between them in the DAG.
Ah, that makes sense. So it's kind of a map of how likely different tokens are to follow each other based on what the LLM is doing in those parallel generations.
Right. And then they do this clever search through the DAG to extract the most likely sequence of draft tokens, starting from the beginning and greedily selecting the next token that has the strongest connections.
And they keep doing that until they hit a predefined length limit for the draft sequence, or they reach a point where there are no more outgoing connections in the DAG.
Precisely. And one of the cool things about using a DAG is that it's more compact than a tree structure because it merges identical tokens that appear at the same step in multiple sequences.
Ah, so it's a more efficient way to represent those points of consensus.
Exactly. And it can also capture multiple potential reasoning paths that might diverge and then converge later on.
Okay, so they've generated this promising draft sequence. Now what?
The final step is verification, which is really crucial for making sure they haven't sacrificed accuracy in their quest for speed.
How do they verify the draft tokens?
They compare each draft token to the token that the original LLM would have generated at that same step by sampling from its conditional probability distribution.
So if the draft token matches what the main LLM would have done anyway, they keep it. Otherwise, they reject it and everything that comes after it.
Exactly. That way they ensure that the final output remains perfectly aligned with the LLM's original capabilities, so there's no loss in accuracy from using speculative decoding.
So did this approach actually work? Did they see significant speed improvements in their experiments?
Oh, yeah, they did. They tested it on a couple of really challenging math reasoning benchmarks, GSM-8K and math. And they used some state-of-the-art LLMs like Qwen 2.57b instruct and Llama 3.8b instruct.
And what were the results?
Well, the key finding was that they achieved significantly higher token acceptance rates compared to the baseline methods they tested against.
Which means less time spent regenerating tokens and a faster overall inference time.
Exactly. And they attribute this higher acceptance rate to the fact that their graph tokens are coming directly from the parallel generations of the same LLM. So the underlying probability distributions are a perfect match, unlike when you're using external resources like a separate draft model or a database.
And that makes sense. It's like they're tapping into the LLM's own internal knowledge about what's likely to come next.
Exactly. And their experiments also showed that their method was generally faster at constructing those draft tokens compared to the baselines, because they're not dealing with the overhead of searching a large database or running a separate model.
They also did an ablation study, right, to see how important each part of their method is. What did they find?
Right, they did. And it turned out that using the DAG structure to organize those candidate tokens was really key for getting good performance, especially when combined with fuzzy matching, which allows them to capture those slight variations in how the LM might express the same idea.
Like x squared versus x to the power of 2, as you were saying earlier.
Exactly. And they also looked at the impact of the sampling temperature and the number of samples being generated. They found that intermediate temperature values worked best because it struck a good balance between sample diversity and the ability to find matching suffixes.
And, not surprisingly, more parallel samples generally led to longer accepted draft sequences, because you have a richer pool of potential draft tokens to work with.
Right, more samples, more consensus, better drafts.
So this is all really promising. It seems like they've found a way to significantly accelerate multi-sample inference without sacrificing accuracy. And that opens up a lot of possibilities for using these powerful reasoning techniques in real-world applications. Now, as we always do, let's shift gears a bit and talk about some potential future directions that this research could inspire.
Yeah, I'm excited about this part.
What are some novel notions that come to mind when you think about the implications of this work?
Well, one thing that really stands out to me is the potential to apply this multi-sample speculative decoding approach to other domains within machine learning, like beyond math reasoning.
So areas where self-consistency or similar multi-sample methods are already being used to boost performance.
Exactly. Things like generating complex code or maybe even scientific text. It would be fascinating to see if the same kind of consensus patterns emerge in those domains as we see in math, or if there are unique characteristics that would require adapting the method.
It's like, could you develop different consensus detectors that are specialized for different types of tokens?
Exactly. Like in code generation, maybe the consensus is more apparent in the structure of function definitions or the naming of variables. And then there's this whole idea of dynamic adaptation. What if we could make the parameters of the method adjust themselves based on the actual level of consensus or uncertainty that's being observed in the parallel generations?
So it's like the model is learning the best way to speed itself up as it's thinking.
Right. Maybe for a really difficult problem, it starts off with a more lenient, fuzzy matching to build a larger pool of draft tokens. And then as the parallel reasoning paths start to converge, it gradually tightens the criteria. That could lead to even greater efficiency gains without compromising accuracy.
That's a fascinating idea. It's like the model is becoming more confident in its predictions as it goes along, so it can afford to be more picky about which draft tokens it accepts.
Yeah, and these are just some initial thoughts. I think there's a lot of room for really interesting exploration in this area.
Absolutely.
Yeah.
So the big takeaway from this paper is that the researchers have come up with a really clever and efficient way to speed up large language models. And it's all about exploiting the information that's already there in the multi-sample inference process. It really does make you wonder how techniques like this might change the game for applications where both speed and accuracy are crucial.
For sure.
We'll make sure to link to the full paper in the show notes for anyone who wants to dig deeper into the technical details. And as always, we'll leave you with a thought-provoking question to ponder. As LLMs become more and more integrated into everything we do, how might these kind of acceleration techniques change our expectations about how quickly we can get answers to complex questions, even when we have limited computational resources? It's something to think about. Thanks for joining us for this deep dive, and we'll catch you next time on TalkTensors.
See you then.